Hello, I am Jenna Sivek, and this is Power in Electric Circuits as found in Chapter 20.4 in the OpenStax physics textbook. Power is often associated with electricity. For units, we often think about power in watts, but what does that really mean? Power, as we learned previously, is defined as the rate per unit of time of energy use in a circuit. Or to put it in a mathematical sense, it is the electric potential energy divided by the time. In the case of electric power, the electric potential energy depends on both the voltage involved and the charge moved. The simplest way to express this is the potential energy equaling the charge moved times the voltage, PE equals QV, where in this case the voltage means the potential difference that the charge moves through. Electric power is the rate at which this electrical potential energy is moved, and so electric power is equal to QV over T. From here, we recognize that electrical current I is equal to the charge moved over time. And so the expression for electrical power becomes P equals IV. Simply, this means that electric power is equal to the current times the voltage. We are familiar with the electrical power unit of watts. Since the SI unit for potential energy is joules, watts are defined as having the units of joules per second. So thus, 1 amp times 1 volt equals 1 watt. This is the relationship between electrical current, voltage, and power. As for the relationship of electrical power to the resistance, we would have to turn back to Ohm's law, which we learned previously. Ohm's law states that the voltage is equal to the current times the resistance. Now, before I move forward, I would like to point out that this equation for electrical power, power equals current times voltage, is valid for all electrical circuits. But these equations, which we will derive using Ohm's law, are valid only for circuits with resistors, which follow Ohm's law. So these equations that I derived are that the power is equal to the current squared times resistance, also that the power is equal to the voltage squared divided by resistance. Different insights can be gained from these three different expressions for electric power. For example, P equals V squared over R implies that the lower the resistance connected to a given voltage source, the greater the power delivered. Furthermore, since voltage is squared in this equation, the effect of applying a higher voltage is perhaps more than we might expect. So when the voltage is doubled to, say, a 25 watt bulb, its power nearly quadruples to 100 watts, burning it out. If the bulb's resistance remained constant, its power would be exactly 100 watts, but at the higher temperature, its resistance is higher too. In this example problem from our homework 3, problem 4, it states what power is supplied to the starter motor of a large truck that draws 195 amps of current from a 24-volt battery hookup. So in this case, we just simply use the equation P equals IV, power equals current times voltage, and we get that the power is equal to the 195 amps times the 24 volts, and that equals 4,680 watts, which is also equivalent to 4.68 kilowatts. In this example from our homework number 4, in the first half of problem number 3, it states, given a 48-volt battery and a 24 ohm and 91 ohm resistors, find the current and power for each when connected in series. So we're presented with a circuit that contains a battery and 2 resistors in series. We know that resistors in series are additive and have the same current. So in this problem, we have to determine the current flowing through and power of each resistor. Since we know that resistors follow Ohm's law, we can use the two equations from electrical power that we derived from Ohm's law. We are given that the voltage source, the battery, is 48 volts, and the resistance of each resistor in ohms, the first resistor being 24 ohms and the second resistor being 91 ohms. To determine the current going through each of these resistors, we can simply use Ohm's law, V equals IR. Solving it for current, we get that I equals V over R. However, since we know that we need to find the equivalent resistance of the series of resistors using R equivalent equals R1 plus R2, and etc., So in this case, our equivalent equals 24 ohms, plus 91 ohms, which equals 115 ohms. Now we can use Ohm's law to determine the current, since it will be the same for both resistors. So the current I is equal to the voltage of the battery divided by the equivalent resistance, 115 ohms, which equals 0.417 amps. And now to determine our power for each resistor, we can use the current and plug it into our equation P equals I squared times R, which is valid for ohmic circuits. So we get that 0.417 amps squared times the resistor, the resistance of resistor 1 equals 4.18 watts. And for resistor 2, we get that 0.417 amps squared times 91 ohms equals 15.85 watts. From this we can see that the power dissipated by resistor 2 is much higher since the resistance is high. High power resistors that can dissipate many watts of electrical power as heat can be used as part of motor controls in power distribution systems or even inside your toaster. Related to electric power is electric energy. We know that the longer we leave on appliances that use electricity, such as lights or computers, our electricity bills go up. This is based on the fact that as we use more power, we use more energy. So the two are related in the equation power equals energy divided by time. And solving for energy, we see that electrical energy is equal to power times time. So it makes sense that the longer we leave on appliances, the more power, and thus the more energy we use, which we are subsequently also billed for. On our electric bills, we see the units of kilowatt hours, which makes sense since we know that our energy is in units of power times time. To reduce our energy costs at home, we know that we can reduce our time using electrical appliances, or we can purchase more efficient appliances, such as LEDs that consume less power over time, helping them last longer than regular incandescent light bulbs. This equation, E equals PT, is also useful when you consider it in other contexts. For example, if you consider the amount of energy that your body uses during exercise, it is related to the power level and duration of your workout. A short, intense workout may cost the same energy as a longer, less intense workout, although they can lead to different results. So in review, we learned that electrical power in circuits comes from the relationship between electric potential, energy, and time, and is simplified to the equation P equals IV, meaning that the power in the circuit equals the current in the circuit times the voltage, i.e. the electric potential from the power source in the circuit. We learned that the equations derived from Ohm's law, P equals I squared times R and P equals V squared over R, are only valid in circuits that use resistors that obey Ohm's law. We also learned that electric energy is related to electric power by the equation E equals PT, meaning that as you increase the time using a certain level of power, your energy will also go up. Thank you for watching.